Okay guys, welcome to our first lesson. Today we're going to start talking about sequences. And we'll start by defining some of the properties of what we mean by the mathematical term sequence. The first property is that a sequence is an ordered collection of elements known as terms. And one of the really important points here is that idea of ordering. In many ways, a sequence can be compared to sets, which we have previously looked at. But in a set, the order of the elements is unimportant. Also, unlike in sets, elements in a sequence may be repeated more than once. Sequences can be of finite length, or they may be infinite. And finally, there is often a rule that defines the progression of a sequence. We'll now take a look at a few examples of sequences to see how they can be generated. The first one we'll look at is simply the sequence of odd numbers. 1, 3, 5, 7, and of course this sequence will be infinite. We could also say that this sequence is generated by adding 2 to the term previous, and that each term is then generated from that previous term by adding 2. In the same way that we can have a sequence generated by addition, we can also have one generated by multiplication. So the next sequence is one where each term is double the one before. Again, an infinite sequence. We could also describe this though as the sequence of powers of 2, as the first term is 2 to the power of 1, followed by 2 to the power of 2, 2 to the power of 3, etc. The next sequence we're going to look at is a famous one called the Fibonacci numbers. Starting with the numbers 1 and 1, each number after that is generated by adding the 2 previous. So 1 and 1 is 2, 1 and 2 is 3, 2 and 3 is 5, 3 and 5 is 8, and so on. The Fibonacci sequence is particularly famous because it crops up in many places in nature. We'll now look at an example of a sequence which is non-numeric or algebraic, starting with the term a and followed by ax, ax squared, ax cubed, and so on. So for each of these sequences, as we were generating them, there was a rule to their progression, and we can write these rules down. So for the first one, the nth term, designated by t subscript n, is equal to 1 plus 2 n minus 1 times. N minus 1 because we need one lot of 2 to get to the second term. We need to add 2 lots of 2 to get to the third term. And we'll need n minus 1 lots of 2 to get to the nth term from the first. The second sequence can be written as term n equals 2 to the power of n. So the first term is 2 to the power of 1, the second term is 2 to the power of 2, etc. The third one is a little different because it's difficult to write an explicit formula that allows us to calculate any particular term in the sequence. Eventually, each term is equal to the sum of the 2 before it. But in order to reach that point, we'll have to define the first 2 terms. So term 1 and term 2 are 1, and then after that, term n is equal to term n minus 1 plus term n minus 2, so the 2 before the term that we're interested in. And in the final case, we're back to something a little bit more easy again. Each term is a times x to the power of n minus 1. So for the first term, it's a times x to the power of 0, which is just a, and then a times x, and then a times x squared, and then a times x cubed. In the first, second, and fourth, as I said, we were able to give an absolute definition for what each term was with one formula. In the third example, though, the Fibonacci sequence, we had to resort to what is known as a recursive definition. A recursive definition defines each term as being somehow connected to the value of one or more previous terms. And so you use each of the terms to generate the next one, and then you use those to generate the next one, and the next one, and the next one. And so you apply the formula over and over and over again recursively in order to generate the whole sequence. Over the next couple of weeks, we will be focused on two particular types of sequences. The first will be arithmetic, and the second will be geometric. Now, both of these types of sequences have very specific properties and rules for how they're generated. And we'll look into those, and we'll also study a number of formulae that allow us to work with them and do various types of maths with them. So that will be over the next couple of weeks. So to recap what we've seen so far, a sequence is an ordered collection of numbers that is made up of many terms and which often progresses according to some underlying rule. A sequence can be finite in length, or it can be infinite. Over the next couple of weeks, we will focus on two particular types of sequences, arithmetic and geometric.